What is dark matter? This is one of the most frequently asked unanswered questions in the whole of physics, and the subject of this video. My name is Alessandro, and I'm a PhD student studying particle physics at the University of Oxford. I work on the ATLAS experiment at CERN, and my research is looking for dark matter particles with the detector. And today I'm going to explain a bit about how we do that. It was found that only 5% of the energy in the universe is normal matter. So what is the rest? 27% is what we call dark matter, and this is likely to be a new particle and is going to be the focus of this video. 68% is what we call dark energy, and the jury is out for potential explanations as to what this is. The standard model of particle physics is one of the most successful theories that humanity has come up with. So could any of these particles be dark matter? Let's start with a full list of particles in the standard model. As our most powerful particle detectors have not yet seen any conclusive evidence for dark matter, we can use this to put some constraints on the properties that any dark matter candidate particle must have. First, they must be weakly interacting, or we would have seen them by now. So this means they can't be charged in any way. No electric charge, no colour charge. So this already rules out the quarks, as well as the electron, the muon, the tau, the W plus or minus boson, and the gluons. They must be stable, so they've stuck around. This rules out the Z boson and the Higgs. So we've already narrowed it down quite significantly. What have we got left? Well, it can't be the photon, because the photon is massless. We need dark matter to have mass. Evidence from the formation of clusters of galaxies in the early universe indicates that dark matter cannot be purely relativistic. This means rules out lower mass particles like the neutrino. We need physics beyond our understanding, beyond the standard model. There are many theories out there that predict new dark matter particles. How can we look for these particles? One of the ways is with a big machine that collides protons like the LHC. The LHC is a 27-kilometer circumference ring of superconducting magnets that accelerates protons and collides them at a record 13.6 tera-electron volts. We need to get information on what is produced, and the detector I work on, ATLAS, is the biggest of the four main detectors at the LHC. We use ATLAS to learn as much as we can about the product of our collision by measuring things like the energy and momentum, and trying to identify what particles we have present in our events. Think about the properties of dark matter. We cannot directly detect it with ATLAS. So we have to infer the particle's existence by comparing what we see with what we expect from the standard model. Most of the energy of the particles will be in the direction of the collision, but some will have energy in the perpendicular direction, the transverse direction. Due to conservation of momentum, all of the energy in this direction should add up to equal zero. If it does not, we can assume that some of the transverse energy was not picked up by the detector and carried away by invisible particles. However, it is not that easy. The standard model has particles, the neutrinos, that can also give this missing energy signal. In practice, finding the Met is a very hard thing to do. We spend a lot of time investigating whether our Met is from neutrinos, misidentified particles, or detector issues. And we use it with lots of other variables to help us look for dark matter. So what have we found? Nothing yet, unfortunately. Up to this point, investigations have put strong constraints on the properties of any potential dark matter candidates. And it's hoped over the next few decades, experiments like ATLAS or other experiments like Lux Zeppelin will be able to finally determine what this elusive particle is.